Hey there, guys. Mr. Carlson here, and let's talk about something called atomic radius. Atomic radius. When we're talking about atomic radius, what we're essentially referring to is the relative size of an atom. Relative size of an atom. Now, here's the thing: the relative size of an atom can kind of change. Um, and based on what type of element that we are dealing with and how many electrons and how many protons that it has. So if we're thinking about the size, it's not um, like if we were to measure like the size of, like, let's say a golf ball or a tennis ball or something like that. We would just look at the edge of it, and we could take a ruler, and we could measure how far is it from the center to the edge of that. It's kind of different with atoms because atoms don't really have a defined edge to them. They don't really have a defined edge. They sort of do, but it's kind of always changing. So remember, the outer edge of an atom would consist of those valence electrons. So if um, let's say I've got an atom here with here's its nucleus with its protons and neutrons. Okay, well, the edge, like if we're thinking of like the edge of a golf ball or the edge of a baseball, like that, the edge for an atom is not really defined. It's more of just that very outer energy level, which, remember, we said um, for that is like the probability of where an electron is. So like for this atom here, the outer edge of it, or what we can think of as the outer edge, is those outer shell, or those valence electrons that are out in the very last or the highest energy level. That's the outer edge of that atom. And so that's how we would think of as the relative size of the atom. Now, here's the thing: the size, or the radius, which would be from here to here, is going to change based on a couple of different things. And there's actually some trends that we see in the periodic table as far as the size of atoms go. The way that we define atomic radius, by the way, so atomic radius is defined as half the distance between, um, we'll say, between nuclei. Ooh, how do you spell nuclei? Nuclei? Between nuclei? Plurus for nucleus? Plural for nucleus? Half the distance between nuclei. So in other words, if I've got two atoms here, so here's the nucleus of one atom, and here's the nucleus of another atom in an element that are bonded together, it would be half the distance between, so here's the distance between two nucleus, and it would be half the distance here. Half that distance, that would be the atomic radius, okay? Now, there are some trends in the periodic table, trends in size, when we look at the periodic table and we look at the size of atoms. Let's talk about first. Remember that the setup of the periodic table, we have groups. So groups are going like this. We have group 1. Whoops, gotta change colors here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? These are my group numbers. We're going to forget about the transition metals for a second. And then we've also got periods. So running this way, I've got period 1, 2, 3, 4, 5, so on and so forth, that are running this way. So periods run across, groups run up and down. Now, if we think about just the groups, or sorry, the periods, so these right here, the periods, each period. If we think about how the size of atoms, or the atomic radius, changes as we move across from left to right across the periodic table, so going from hydrogen to helium, or starting with lithium and then moving across over to neon we're starting with sodium here and moving across. What do you think, if you had to guess, do you think that as we move across a period that the atoms get bigger? Or do you think that the atomic radius will get smaller as we move across a row? And maybe try and think, why would that be? You know, what would cause your atoms to get bigger as you move across? Or if you think that they get smaller, what would be causing that? And what we actually see in general, the trend is that as we move across a period, what actually happens is that the size actually decreases, gets smaller. As you move across a period, the size, the atomic radius actually decreases. So going from hydrogen over to helium, hydrogen is actually going to have a little bit bigger radius than helium does. And in period 2, lithium is going to have a bigger atomic radius, going to have a bigger size than neon is going to have. And same thing if I go down here with sodium. Sodium is going to have a bigger size than argon is going to have. So it's going to move and get smaller and smaller as we move across. And we can follow that pattern all the way down. Now again, that's in general. So there are some exceptions to that rule that we find in the periodic table. But in general, as we move across a period, the size decreases. It gets smaller and smaller as we move this way. In fact, let's make sure we write that down. So we're going to say, in general, as we move from left to right, across a group, or sorry, I always get those mixed up, across a period, the size decreases. Now, what about, so that's looking at a period. Let's think about, what about if I were to start at the top of a group? So instead of going across a period, but if I were to start at a, let's say group 1 here, group 1, what do you think is going to happen to the size of these atoms as we move down a row? So we just said that as we move across, they decrease. What do you think is going to happen as I move down a row? And why do you think that's going to happen? And actually, before we answer that, let's take a step back and think about why it is, first of all, because we didn't answer this, but why is it that the size decreases as I move across? So let's take, for example, lithium and neon, right? Why is it that as I move across a row that the size will get smaller? Because if I think about it, neon actually has a bigger mass, doesn't it? It has a higher atomic number, it has a higher atomic mass. If you look at the periodic table, it's got a higher atomic number, it's got a higher atomic mass. And so you would think that if it's got a higher mass, why is it that it's smaller, that its size is smaller? And if we think about it like this. In period 2 here, we just got done learning about that all of these elements in period 2, they are all filling up the second energy level with electrons. So lithium, its valence electrons are in the second energy level. Same thing for neon. All of its valence electrons are in the second energy level, right? But each of these has different amounts of protons. So let's take a look at lithium. It has 3 protons, right? So 1, 2, 3. That's 3 positive charges. And it has, so we'll put, here's the first energy level with its electrons, and then it's got that second energy level, right? But neon has, so it's going to have 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons. That's 10 positive charges in the center of that nucleus. But again, it only has 2 energy levels for its electrons. Okay? But here's the thing. So here's lithium's valence electrons, and here's neon's valence electrons. Well, since neon has 10 positive charges in the center, it has much more of a pull. It has much more of a pull because remember, opposite charges attract, right? And these electrons are negatively charged. These protons are positively charged, and so these are pulling down. They're pulling on them with a force. There's a we can think of as a magnetic force. Same thing here. These are positively charged. These are negatively charged, and so they feel a force pulling it in. Right? They feel an attraction towards this. These have way more positive charges. Neon has more positive charges pulling in, and it only has 2 energy levels away for electrons, same distance here, but because this has more of a pull, that means it pulls these electrons just a little bit closer, and so therefore the size of this atom actually is smaller, which I didn't draw to scale because this one should actually be drawn a little bit bigger, but for neon, because it's got more positive charges pulling in on those electrons, that's why it's smaller, and that's why we see that trend as we move across, because as we move across, we're adding protons. We're adding a proton, 1 proton each time, but we're not changing the distance away that those electrons sit at their energy level, and so there's more of a pull. So now thinking about that with this, moving down a group, what do you think is going to happen there? And actually what we see here is that as we move down this way, down a group, is that the size actually increases. And so the reason for that, the reason why if we move down, so lithium is going to have a bigger size than hydrogen, sodium is going to have a bigger size than lithium, so on and so forth. As we move down these rows, like argon is going to have a bigger size than neon, and neon's going to have a bigger size than helium. Again, that's in general. There might be some exceptions, but in general, as we move down a group, we increase the atomic size. And think about it like this. Like if I look at hydrogen and then I look at sodium, for example, as we move down a level each time, we're adding another energy level for our electrons. So if I've got hydrogen and lithium and then sodium, think about this. Hydrogen only has an electron in the first energy level. That's it. Lithium has 2. Sodium has 3, right? It's at period 3 here, so it's got 3 energy levels. And so as we move down, we keep adding another energy level for those valence electrons. And so therefore, that atomic radius is going to get bigger and bigger and bigger, essentially. So we are adding protons each time, but the distance at which the valence electrons keeps getting farther and farther away. And so as we move down this way, it's going to increase. So let's go back over here and say, we'll add to this. Let me increase this a little bit. So in general, as we move down a group on the periodic table, as we move down a group on the periodic table, the size increases. Size increases. And that's all I wanted to cover today, is these trends in size and why we see those trends in size. In fact, I forgot to even show this right here. This is the periodic table showing the atomic radiuses. So it's showing you, here's the entire periodic table, and it's showing you the actual relative sizes of atoms, and we can actually see right? That as I move, if we just look at moving from here to here going across this way, you'll see that they start to get smaller and smaller in general, right? In general, there's a few exceptions, especially here in the middle with the transition metals, but as you move across, they get smaller and smaller. But then as we move from top to bottom, if we're looking at just a group, right, they increase in size. So decreasing in size going this way, increasing in size going this way. So with our biggest atom kind of in the bottom left and our smallest one in the upper right, essentially. So I guess you could also think about it kind of in a diagonal way like this. But so that's our trends in size.